Welcome back to today's session. Hope you people are at home and being safe. As I had discussed in the discussion, we'll be starting off with a new concept from today onwards. It is assignment problem, which is actually a special case of linear programming. So this assignment problem you will encounter in multiple subjects, like in your advanced algorithms also you will be studying this. But the algorithm or the procedure that we use to solve the problem is different. In linear programming, to solve assignment problem, we make use of a specific algorithm called Hungarian algorithm. So here we would be studying assignment problem as a special case of linear programming, and we will solve the problem using Hungarian algorithm. So first of all, let us understand what is this assignment problem. An assignment problem seeks to minimize the total cost assignment of m workers to m jobs, given that the cost of worker I performing a particular job J is given by Cij. In simple terms, if at all I have to explain it, see, let me assume there are some three jobs that have to be done, and we have three different workers available, and each job can be done by a single worker, and every worker can do only one job. So this is the constraint applied on us. So we are supposed to assign these jobs to the workers in such a way that the assignment cost will be minimized. See, every worker is capable of doing all the three jobs. So worker 1 might charge 5 rupees for job 1, 6 rupees for job 2, and 10 rupees for job 3. The second worker might charge maybe 6 rupees for job 1, 5 rupees for job 2, and 8 rupees for job 3. And the third worker might charge 6 rupees for job 1, uh, 8 rupees for job 2, and 5 rupees for job 3. So we are supposed to see to it that all the jobs are assigned to the workers. That is, the three jobs are done by three different workers. It is assigned in such a way that the cost, the assignment cost, or the cost in which the cost incurred through which we are assigning the jobs should be minimum. These costs for each worker I performing a particular job J is denoted by Cij. Fine. So it assumes all workers are assigned and each job is to be performed. An assignment problem is a special case of linear programming problem. Hence, assignment problem can be solved by formulating it as a linear program problem. Right? Here, what we do is this scenario, whatever I explained now, the assignment problem, we will try to convert it or formulate it as a linear programming problem and then try to solve it. To understand the problem better, the graph representation of an assignment problem with three workers and three jobs is shown in the next slide. Whatever I explained now, that I have shown it graphically in the next slide. So have a look at the assignment problem here. These are all the workers. I have three workers, worker 1, worker 2 and worker 3. Similarly, I have three jobs, job 1, job 2 and job 3. Every worker is capable of doing each of the jobs. So worker 1 charges C11 to do the first job. Worker 1 charges C12 to do the second job. Worker 1 charges C13 for doing the third job. Similarly, worker 2 has individual costs C21, C22, C23 for the 3 jobs. Worker 3 has the cost assignments of C31, C32 and C33 for the individual jobs 1, 2 and 3. We are supposed to assign the jobs in such a way that one worker gets only one job and every job is done by a single worker. So that means to say we are supposed to establish a one-to-one relationship for the workers and the jobs in such a way that when you add up all the costs, right? When you add up the assignment costs, it has to be minimum. Hope you have understood the concept of assignment problem. The structure of assignment problem: let C be an n cross n matrix. Why n cross n? Because the number of jobs that we have and the number of workers that we have is the same. Therefore, it will be a square matrix using which we represent. Let C be an n cross n matrix representing the cost of each of the n workers to perform any of the n jobs. So I have n workers, n jobs, then the cost matrix will be a n cross n square matrix. The assignment problem is to assign jobs to the workers so as to minimize the total cost. Clear? So this is the objective. Since each worker can perform any one job and each job can be assigned to any one worker, the assignments constitute an independent set of the matrix C. Fine. So this is just to show you the structure of how the assignment problem looks like. Let me assume P, Q, R, S are the jobs, A, B, C, D are the workers. So individual costs are given, right? This cost represents worker A charging for job P. This represents the cost of worker A on job Q. So whenever I have 4 jobs and 4 workers, then the cost matrix will be a 4 cross 4 matrix. What is our task then? We are supposed to identify the assignment, right? We are supposed to assign which job is assigned to which worker. So the one which is highlighted, if at all I treat it as assignment, this is one possible solution for our assignment problem, right? Uh, Worker A is doing job Q, worker B is doing job S, worker C is doing job R, worker D is doing job P. The reason why I have shown some arbitrary assignment here is because I wanted to show you how the cost is calculated, total cost is calculated. See here, the total cost of assignment will be, for the first assignment, the cost was 2. So 2 plus 8, 10, 10 plus 9, 19, 19 plus 4, 23. So this total cost for this assignment that we have seen is 23. Assume if at all I had made an assignment here, A to P, then the cost would be 1. Then if at all I consider B to Q, so 1 plus 4, it would be 5. Then if at all I make an assignment C to R with 9, so 5 plus 9, 14, 14, and the last option left out is 16 here. 14 plus 16 makes it 30. So it will make it a costly assignment, right? So there are multiple possible solutions that are available. As I said, multiple feasible solutions will be available. My objective is to optimize or minimize the total cost of assignment. That is why we say it as a special case of LPP. Like in LPP, every problem has a lot of feasible solutions. Out of the feasible solutions, we are supposed to identify the best possible solution, and we call that as the optimal solution. And do we have constraints here? Yes. Like in linear programming, here also we have constraints. What is the constraint? Can one worker do two jobs? No, not possible. So the first constraint that we have is every worker gets only one job. Similarly, with respect to jobs, if we have a look, can one job be assigned to multiple workers? That is also not allowed. So one job has to be done by a single worker. So this is another constraint. So here also we have constraints like in linear programming. Therefore, I call it a special case of linear programming. So how do I interpret these constraints with respect to the problem? If we have a look, what does the constraint mean? See, constraint with respect to workers, if you have a look, every row can have only one assignment. That means to say every row can have one assignment. This is the first constraint. Now constraint with respect to jobs, if we have a look, every column can have a single constraint. No column can have more than one constraint. No row can have more than one constraint or more than one assignment. Sorry. So these are the two constraints that we have. What are we trying to optimize? Optimize the total assignment cost. That is summation of all the assignment costs Cij. Fine. So we will look at the mathematical modeling part of this, mathematical modeling of the problem or formulation of AP as an LPP. Given the cost matrix C, which lists for each worker I the cost of doing the job J, right? So I have a matrix C. For every worker I doing a particular job J, I have a particular cost Cij associated with it. The solution for this problem will be a permutation matrix. So for a particular job, a particular worker is assigned. So this is a permutation of all the possibilities. So each permutation I denote by an X, and all zeros except for one in each row and one in each column. So this permutation matrix X can have only one X in each row and one X in each column. So that is the constraint applied that I just explained in the previous slide. What is the objective? The objective is to minimize the total cost, right? How do we denote the total cost? So it is Cij. So if at all I consider summation of Cij, then all the costs will get added, not the costs which has assignment. So what I do is I assume the assignments to be denoted by a binary variable 0 and 1. If it is assigned, it will be 1. If it is not assigned, it will be 0. So for every cost, when I multiply it with the assignment factor, if it is not assigned, it gets multiplied by 0, so resulting in a 0. Only wherever I have an assignment, it will have 1. When I multiply with the cost, I will get the cost itself. So therefore, the objective is to minimize the total cost, which is C total is equal to summation of Cij into Xij, where Cij is the cost, Xij is the assignment factor. Fine. So we will have a look at the mathematical modeling here. Let Xij, as I said in the previous slide, Xij is an assignment factor that I am using, which will be binary. It will be 1 if the resource I is assigned to activity J. That is, if worker I is assigned to the job J, then it will be 1. Otherwise, it will be 0. And what is the objective? The objective is to minimize z equals double summation of Cij Xij, subject to the constraints. Summation of Xij, row wise I am finding the summation. It has to be equal to 1. So in a row, I can have only one assignment for I is equal to 1 to n. So each resource is assigned exactly to one activity. Similarly, column wise, if at all I look at the constraint, so it will be summation of xij, but here the variable, this was j representing each row. Here I am using the variable I representing each column. So summation of xij should be equal to 1. With respect to a column, if at all I add the assignments, it has to be 1. That is, each activity is assigned exactly to one resource. Fine. So this is how we formulate or mathematically model your assignment problem. This is called the mathematical modeling of assignment problem or formulation of assignment problem as linear programming. Okay. So we will just have a look at how the problem looks like. 4 machines are available to process 4 jobs. 4 machines A, B, C, D are there. There are 4 jobs 1, 2, 3, 4. The processing time for each machine or machine per job assignment is as follows. It is not always the cost, it can also be the processing time. So the variable that I consider need not be cost all the time, it can be the processing time as well. Fine. So the processing time is given. When machine A is doing job 1, it takes 4 minutes. Machine A is doing job 2, it takes 6 minutes. So similarly, I have a processing time matrix, which in general we call it as the cost matrix. So we are supposed to find out the assignment to minimize the total processing time. So how does our LPP look like? If at all we try to have a look at the LPP part of it. So I am taking summation of Xij, Cij. Cij is the matrix itself, 4, and Xij is denoted by x11, x12, x13, x14, so on. So 4 into x11 plus 6 into x12 plus 5 into x13 plus 5 into x14 plus 7 into x21 plus 4 into x22 plus 5 into x23 plus 6 into x24. So what I am doing is I am multiplying each of these terms with xij and adding it up, and I want this to be minimized. So this is my objective function. So here one thing that we see is for a particular row, if at all I consider, that is x11, x12, x13 and x14. Out of these 4, only one of the x values will be 1. The remaining will be 0. If at all I consider column wise, out of this x11, x21, x31 and x41, only one of them will be 1. The remaining will be zeros. Right? So that is the constraint. So that sub constraint I am showing here. So x11 plus x12 plus x13 plus x14, that is the first row, should sum up to 1. So only one of them will be 1, the remaining will be zeros. So similarly, second row constraint, x21 plus x22 plus x23 plus x24 is equal to 1. x31 plus x32 plus x33 plus x34 is equal to 1. That is the third row constraint. x41 plus x42 plus x43 plus x44 is equal to 1 is the fourth row constraint. Now we come up to the column constraints. x11 plus x21 plus x31 plus x41 should be equal to 1. Similarly, second column constraint, x1 2 plus x2 2 plus x3 2 plus x4 2 is equal to 1. So similarly for the third column and fourth column also we write. So this is the expanded form of your LPP. This is your objective function and this is your constraint. And obviously you will have non-negativity constraint also. The non-negativity constraint will say that your variable xij should be greater than equal to 0. That is already decided. Xij must be either 0 or 1. So obviously it will be greater than equal to 0. So non-negativity constraint part is also satisfied. So therefore assignment problem is a special case of LPP. So what are we basically trying to do in the assignment problem? We'll just recap once. Our basic uh, objective or the motto of solving the problem is, can you find a lower cost assignment? We are trying to find out the minimum most cost assignment. Can you find the minimal cost assignment? And remember that each assignment must be unique in its row and its column. That is, in each row I can have only single assignment. In each column I can have a single assignment. So this is what your assignment problem is all about. Hope you people have understood what is assignment problem and how does it look like. In the next session, we will be looking into the Hungarian algorithm and try to solve one or two problems so that you can understand it better. Till then, thank you. Have a nice time. Enjoy. We'll come back again with the next video to disturb you. Thank you.